we're going to talk about the spectroscopic terms of an atom. First, let's talk about the different quantum terms of an atom. We have N, L, M, and Ms. N is the different energy levels of the electron, which we know are 1, 2, 3, etc. L are the different angular momentum values of that electron for the different energy levels. So L can be 0, 1, 2, 3, and L is defined in new terms, so to not confuse it with the N. So the 0L is called S, the 1L is called P, the 2L is called D, the 3L is called F. The M are the total possible orientations, angular orientations of each electron. This ends up to be 2L plus 1. So, for example, when L equals 0, you have one total possible configuration for the electron. Ms is the spin orientations of that electron. Ms can equal plus or minus 1/2, which we later will see by the Pauli exclusion principle that no two electrons can have the same spin orientation in one energy level. So, now we're going to see if we can draw these terms for an atom. So I'm going to draw a few different energy values or energy states for any particular atom. Now we have the different angular momentum values too, where this point on the angular momentum value is the point at which all the energy is azimuthal and the electron is orbiting around the nucleus. Now, for the n equals 1, we want to write these in terms of N, L, J, where N is our energy level, L is our angular momentum value, which moves by steps of h bar, and J is our third component, which is defined as L plus S, L being the angular momentum value, S being the spin value. So, we want to define these for each of the different energy states. For the 1 state, n equals 1, L must be less than or equal to n minus 1. I forgot to mention that earlier. But if n equals 1, L can only be 0. So when L equals 0, our angular momentum value is S. J, being L plus S, is 0 plus 1/2, which is 1/2. 0 minus 1/2, which is negative 1/2, which is less than 0, so we can't use that one. So 1s 1/2 is our only orientation of this electron in the n equals 1 energy level, which makes sense according to M. Since L equals 0, our highest L equals 0, 2 times 0 plus 1 is 1, and there's only one state, so it makes sense. N equals 2, what are our possible values? Well, our first N is 2. Our L can be 0, right, because 0 is less than 2 minus 1. And our L can also be 1. When L equals 0, we still have S as our angular momentum value, and J is still going to be 1/2 as our only option. When L equals 1, P is our new angular momentum value. Our new J is going to be 1 plus 1/2 and 1 minus 1/2. So we get 3/2 and 1/2. So 2p 1/2 and 2p 3/2 are the new levels that arise from that. Does that make sense? Checking with M, we have 2 times 1 being our highest L value is 2, plus 1 is 3, and we have 3 different values for the n equals 2 energy level. Makes sense. N equals 3, we'll do one more. We have our N being 3. We have our new L L can still only be, or L can now still be 0, in which S is still going to be 1/2 as we showed earlier. L can also be 1, which is P, where our J's can be 3/2 and 1/2, which we already showed. But L can also equal 2, since 2 minus 1 is 1, which is still less than our energy level, which is 3. So when L equals 2, still have our N equals 3 in this form. Our new L equals 2, so we have D now, and our J equals 2 plus 1/2, which is 5/2, or 2 minus 1/2, are two different spin values, which is 3/2. So 2 more terms arise from this, 2D 3/2 and 2D 5/2. Check with that with our M, so our highest L value is 2, so 2 times 2 plus 1 is 5, and we have 1, 2, 3, 4, 5 different energy levels for our N equals 3 energy value. Sorry, 5 different electron states for our N equals 3 energy level. This is our N equal 1 energy level, our N equals 2 energy level, and this is our N equal 3 energy level for an atom.